This video is to go over the solutions to the tests on limits and continuity. My hope is this will show you the thought process involved with solving problems and to demonstrate the correct formatting in solving those problems. Number 1, state the intermediate value theorem. If f is a continuous function on the closed interval between a and b, and k is any number between f of a and f of b, so assuming a has a point with a y value f of a on the y-axis, b has a corresponding point f of b on the y-axis, and we say for any k value between the two, so any y value that is between these two, well, if it's a continuous function, no matter how you draw your graph between the 2 points, it must cross this line y equals k. At some point c, there exists a c in the interval such that f of c equals k. Part A, true or false, f of negative 1 is less than 0 and f of 2 is less than 0, then there is a point c in the interval negative 1, 2 with f of c equal to 0. We're in the interval negative 1 to 2, and we said the first one is some negative value. F of negative 1 is some negative value. F of 2 is another negative value, f of 2. So intermediate value theorem only tells us we're going to cross one of these points between the two, and y equals 0 is not between the two. So it is false that we will have a 0 between those two values. If f is not a continuous function on AB, then everything is voided. The intermediate value theorem does not apply, because if it's not a continuous function, then we might have a jump and we don't have to cross the k value. So it is true that if it's not continuous, we cannot apply the intermediate value theorem. Number 2, what are 3 different scenarios in which the limit of a function fails to exist? So the first one being f of x approaches a different number from the left than from the right. So if we approach a different y value from the left and from the right, it fails to exist. Number 2, f of x increases or decreases without bound. If at a point x equals 0, we have a vertical asymptote, the limit also fails to exist. And f of x oscillates between 2 fixed values as x gets closer to a point. So as we get closer and closer to the point, we oscillate closer and closer. We're not converging to one single y value, in which case the limit will not exist at whatever that x value is. The second part of number 2, how can you use left and right hand limits to prove that the limit exists at x equals c? If the left hand limit equals the right hand limit, then the limit exists. So vice versa. So if this symbol means if and only if the left hand limit equals the right hand limit, then the limit exists, and that's how we'll use it to prove the limit exists. Number 3, what is the definition of the continuity of a function at a point x equals c? Well, it must pass 3 things. First, the function must be defined at c. Second, the limit must exist as x approaches c. And finally, the limit from the left and from the right must equal the actual value. So we can't have a dot somewhere else. The dot has to be right in the middle, connecting the two. That's how we know it's going to be a continuous function. So, true or false, if a function f of x is continuous at x equals c, then the limit as x approaches c exists. If it's continuous, yes, the limit must exist. So this is true. Okay, if the limit as x approaches c of f of x exists, is that sufficient to show f of x is continuous at the point? The answer is that is false, because that is only one of several of the conditions. It might not be defined there, even though the limit exists. Number 4 is a graph interpretation problem. Find f of negative 4. So we go here, when x is equal to negative 4, along this line, what is our actual y value? The y value is 2. At x equals negative 4, so along this line, what is the limit as x approaches negative 4? So as we approach from the left, looks like we're approaching y value of negative 1. As we approach from the right, looks like we're approaching the same y value. So they agree the limit is negative 1. Is f continuous at x equals -4? Now that we know that it is defined at -4 and the limit exists at -4, we need to see that the limit is equal to the points. And in fact, they are not equal. One is 2, one is -1. Okay, so we have a hole there. No, it is not continuous. Part D, find f of 0. So at x equals 0, our point is defined up here. There's a hole down below. We want to know where is the actual point, and the answer is at 1. Now, what is the limit as x approaches 0? So as we approach this line, x equals 0. From the left, we follow our function. It looks like we get 1. And from the right, if we follow our function, we get 0. So they do not agree. We say the limit does not exist. Find f of 3. So in this case, we have along this line, when x equals 3, what is our value? And it is undefined. There is no point on our graph at x equals 3. Part G, as we approach 3 from the right, our function is approaching -infinity. So the limit does not exist, but -infinity is the manner in which it does not exist. H, for what values in the domain is f of x equals 0? F of x is the y value, so the y value is 0 along this line, and the only point is this point, x equals -5, that is defined on that line. List the values C in the domain for which f of x is not continuous. So as I go along my graph, I have to jump up here, so it's discontinuous to there at -4. I have to jump at -2. I need to jump at x equals 0. I need to jump at x equals -3, and I need, or +3, and I need to jump at x equals 4. Those values for which is not continuous is -4, -2, 0, 3, 4. Part J, list the intervals in the domain for which the limit as x approaches c of f of x exists. Now, wherever the function is continuous, the limit also exists. I just need to investigate the same few points, these x values, okay, to see if the limit exists there. And the point is, the limit exists at holes. The left-hand limit equals the right-hand limit here, so I really don't care about that value. The limit exists there. The limit does not exist at x equals -2 because the left-hand limit does not equal the right-hand limit. So everywhere from -infinity to -2, the limit exists. Now everywhere between -2 and 1, but then we have a jump discontinuity again. So the limit doesn't exist there. So the interval from -2 to 0, it exists, union. Over here we have the interval from 0 to 3, and the limit does not exist at 3 because it's unbounded. Finally, the interval from 3, does my limit exist at 4? And the left-hand limit equals right-hand limit, so yes, it does. So the limit exists all the way up to infinity. Number 5, consider the function f of x equals -x plus 1 all over x squared plus x. Well, first thing, before we graph these and analyze them, we want to reduce rational functions. If we factor in x from the denominator, you'll find that if factor x plus 1 cancels, our function is equal to -1 over x, only you have to specify that x cannot equal -1 because it would make the original undefined. It is undefined at 0 also, x cannot equal 0. Now, after we reduce it, that is a vertical asymptote at x equals 0. So I'll draw that in red here. This is a vertical asymptote that we cannot cross. And at x equals -1, there's a hole in our graph because the factor canceled. The other thing is the degree of the numerator is smaller than the degree of the denominator, so that means we're going to have a horizontal asymptote here at y equals 0. And if we plug in a few points, for instance 1, you're going to get -1, and you plug in some other points on the right hand side, you'll get a graph looking like this. On the other side, very similarly, only we have a hole at x equals -1, and our graph looks the same across the origin. So across the origin, these look symmetric across the origin. That is symmetry. Okay, and those are odd functions. And the way you test that is you say, is f of -x equal to -f of x? So we plug it into our function, and the answer is 1 over x, which is in fact -f of x, which confirms it is an odd function. where is it undefined, and is both undefined at x equals 0 because of a vertical asymptote, and x equals -1 because it makes the denominator 0 in the original function. Number 6, f of x is a piecewise function that is a quadratic when x is less than 1 and is this linear function when x is greater than 1. We want to determine what is the limit as x approaches 1. Well, does our left-hand limit equal our right-hand limit? So our left-hand limit as x approaches 1 from below, we're really talking about this interval when x is less than 1, which means our function takes on the upper function x squared plus 5. This is a polynomial, so we can do direct substitution, meaning x is approaching 1 from below. So we get 1 squared plus 5, and the answer is 6. Our left-hand limit is 6. For the next one, we want to find the right-hand limit as x approaches 1 from above of f of x. So the x values are then always greater than 1. So our function takes on the values of the line -2x plus 8, which is a line polynomial. So direct substitution applies. We're doing -2 times 1 plus 8, and the answer we get is 6 once again. Left-hand limit equals right-hand limit. The limit is 6. Number 7, find the limit as x approaches 5 of cosine of pi x over 6. Does direct substitution apply? And the answer is yes, because we can apply direct substitution wherever trigonometric functions are defined. Cosine is defined everywhere. Cosine of pi times 5 over 6. Either use your calculator or remember from trig, cosine of 5 pi over 6 equals -√3/2. 8, find the limit as x approaches 0 of sine x to the 4th power all over x cubed. And this looks a lot like the trigonometric limit we have memorized. We split up into sine x times sine x times sine x times sine x, and over x times x times x. And we know that the limit of the first one as x goes to 0 is 1. The limit of the second one as x goes to 0 is 1. And the third one is also 1. And sine of x as x goes to 0, well, it's defined everywhere, so we plug in 0 and we say sine of 0 is 0. So we have 0 times 1 is 0. Find the limits as x approaches 5 from below of 2x minus, and this is the greatest integer function. The greatest integer function means whatever number is plugged in, for instance 4.9, was the greatest integer that's smaller than it, and the answer would be 4. Okay, so I'm going to do direct substitution to see what happens. Now, if I plug in something slightly smaller than 5 for both the x's, then I get 2 times 5 is, well, 2 times something slightly less than 5 is just slightly less than 10. Okay, so we approach 10 from below, minus, and no matter what I plug in here, it's always less than 5, which means we have to round it down to 4. Be having 10 minus 4, and the answer is 6. We want to find the vertical asymptotes of the function tangent of 15x, which is the same as sine of 15x over cosine of 15x. And we're going to have vertical asymptote whenever the denominator equals 0, when this is 0, and the numerator is not equal to 0. Okay, so cosine of something is equal to 0, pi over 2, 3 pi over 2. Basically, the spacing of the vertical asymptotes is pi apart. We're going to multiply integers by pi. So 0 pi, 0, 1 pi, -2 pi. Okay, all those values, but we want to shift it over to right pi over 2, so we add pi over 2. So cosine is equal to 0 at pi over 2, and at, this makes 3 pi over 2, and this makes -3 pi over 2. All of those values, but for any k that you want to plug in. That's when cosine has a vertical asymptote. We're taking cosine of 15x. So we want to find the x values for which this has a vertical asymptote, which means we really want to just divide both sides by 15 to get x by itself, and then we end up getting k pi over 15 plus pi over 30. We get a common denominator, and x equals 2 pi k plus pi over 30, and we can factor out a pi. X equals 2k plus 1 over 30 times pi. So the answer is B. In Show Your Work problem number 1, we are to use rectangles to graph the region bounded by the graph y equals 4 over x, y equals 0, x equals 1, and x equals 4. We want to find or approximate the area of that region. Now, we're going to do this with rectangles, and it looks like we're using 6 rectangles. We're going to find the area of each rectangle. The first rectangle here has a width of 1/2, and it has a height that is determined by the y value of our function at x equals 1. So we plug 1 into our function here, and we get 4 over 1. Our next rectangle, we want to find the area of this rectangle, and the width is the same as 1/2. In fact, the width of all of our rectangles is 1/2. But the height is given by our function. The y value of our function is 4 over whatever x value that corresponds to. That x value is 1.5. So our next rectangle, the height is given by the y value of our function at x equals 2. So 4 over 2 times the width is 1/2. Our next rectangle here, and the y value is given by our function 4 over, and that x value is 2.5 times 1/2 to give us the area. And the next rectangle, the y value at x equals 3 is 4 over 3 times 1/2. And knowing when the stop is pretty important, our last rectangle is our 6th one, and our y value is 4 over the x value 3.5. At that point, you just use your calculator and you want to round your answer to 3 decimal places. If you start rounding some of these answers a little too early, you're going to be a little inaccurate. So please make sure not to round until the very end. Is this an overestimate or an underestimate or neither? So we found the area of these rectangles. If I add those all together, well, we have a little extra. We have an extra piece right here. All of these are extra areas we included. That is more than the area that we had intended. So we're going to say this was an overestimate. Number 2, find the limit if it exists as x approaches 3 of square root of x plus 1 minus 2 all over x minus 3. So what we tend to do with these is apply direct substitution and see if that helps at all. So if we plug 3 in for the x's, we end up getting square root of 4 is 2 minus 2 is 0 over 3 minus 3 is 0. This is indeterminate form. What that means is our limit may exist or may not. We need to do some algebra to see if we can simplify this so we get a definite answer. If you have 2 terms on either numerator or denominator, one's a radical, the trick that we tend to do is multiply by the conjugate of the radical expression. Square root of x plus 1 plus 2. And we cannot change our expression, so you must do the same thing at the top and bottom. Because we're multiplying by 1, it remains unchanged. Now, as you go along here, you have to rewrite the limit every time until the limit is actually applied. So you FOIL the numerator, and get square root of x plus 1 times square root of x plus 1 is x plus 1. And then the 2 middle terms of the FOILing will cancel. And then we'll get negative 2 times 2 is negative 4. Okay, on the bottom, I'm just going to leave it factored. And it's usually going to be nicer to leave things factored and not FOIL them on the denominator because some factors may cancel out later on. In fact, they usually do. So I'm still writing the limit because I haven't applied it, and we have x minus 3 over x minus 3 times square root of x plus 1 plus 2. What happens is our factors of x minus 3 is reduce. We're well on our way, and now we have the limit as x approaches 3 of 1 over this radical expression. Does direct substitution apply? The answer is wherever our functions, rational functions and radical functions are defined, they apply. So if we apply direct substitution, now I don't have to write my limit because it's being applied. And the answer is the limit is 1/4. Part 3, use the 3-part definition of continuity at a point to test the continuity of the function x squared minus 1 over x plus 1 at x equals negative 1. So first of all, is our function, is it defined at -1? And the answer is no, it is undefined there. Which already means the function is not continuous at that point. I'm going to go through the rest of it just for fun. So number 2, does the limit exist there? We first do some algebra because we'll get 0 over 0. So to see if the limit exists, we factor the numerator over x plus 1. One of the factors reduced out. We can apply direct substitution to get -1 minus 1. So the limit equals -2. Yes, the limit exists. But is the limit equal to the value? No, because the value is undefined. It fails 1 and 3, and if it fails any of them, then we say it's not continuous at that point. Find the limit, if it exists, as x approaches 0 of 1 over x plus 4 minus 1/4 all over x. We always apply direct substitution just to see what happens there. As x goes to 0, we have 1/4 minus 1/4 over 0. We get 0 over 0. So anytime that happens, it's indeterminate form. We need further investigation to see if the limit exists. We're going to use any of the rules from algebra to simplify this expression. This is a complex fraction. We're going to see if we can get rid of this and make it a single fraction. In order to do that, I need a common denominator. I'm going to multiply the first fraction by 4 over 4, and the second fraction by x plus 4 over x plus 4. Over the common denominator, now we have 4 times x plus 4 as the common denominator. So then I can subtract the numerators, right? The numerator being 4 minus x plus 4. It's all over x still. As you distribute the minus sign, we end up with 4 minus x minus 4, and 4 minus 4 is 0. We still have the 4 times x plus 4. This x on the denominator divided by x is the same thing as multiplying by 1 over x. On the next line, we still have negative x on the numerator, but now we have 4x times x plus 4 on the denominator. And in fact, we can reduce this even further. The x is reduced, and we get the limit as x approaches 0. And I have to write the limit every time until it's actually applied. 4 times x plus 4. And now I'm going to try the limit out and apply substitution. I can do that to any rational function everywhere it's defined, and it is defined at 0. So we get 1 over 4 times 4, and the limit is 1 over 16. Number 5, consider the function x squared minus 6x plus 7 all over x squared times x minus 3. Determine the points of discontinuity. Rational functions are continuous everywhere they're defined. So where is f of x undefined? Well, where the denominator equals 0. So x equals 0 and x equals 3. Provide the equation of vertical asymptotes. So vertical asymptotes are wherever non-canceling factors of the denominator are 0. So you need to try to factor the numerator, and we'll find out it's unfactorable. So because none of the factors cancel in the denominator, that means x equals 0 is a vertical asymptote, and x equals 3 is also a vertical asymptote. Finally, we want to find the limit as x approaches 3 from below. I'm just going to apply substitution and see what happens. So x approaches 3 from below. It approaches 9 from below, but I don't really care because it's approaching 9. Okay, when you care is if it's 0, because below means negative, above means positive. 6 times 3 from below, we're really approaching 18 there. 18 from below, but we don't care. It's approaching 18. Okay, plus 7 all over, and 3 from below squared, we're approaching 9 from below. Okay, but where we really do care is here. 3 minus 3 is 0, but we really care now that we're approaching 0 from, well, it's slightly less than 3, so like 2.9 minus 3 is negative. So we're approaching 0 from below here. That gives us 9 minus 18 plus 7 is negative 2. Now 9 times 0 is 0 from below. But the point is we have a negative number divided by negative number. So the answer is going to be positive if 2 is constant, right? But as we approach 0, this number is exploding up to positive infinity. The limit does not exist, and positive infinity shows the manner in which it does not exist. Number 6, use the epsilon delta definition of limit to prove limit as x approaches 6 of f of x minus 1 equals 41. So this is really the limit as x approaches c of f of x equals L. We want to show that whenever we're within a delta distance of c, that the y value is approaching the limit, is within epsilon of the limit for any epsilon greater than 0. So meaning we can get arbitrarily close. In order to prove this, first we need to establish a connection between our two absolute values. So we'll start off with the second one. The function is 7x minus 1. We subtract the limit 41, and so we end up getting the absolute value of 7x, negative 1 minus 41, negative 42. Okay, we can factor out a 7, and we get absolute value of x minus 6. So now I see the connection here with the absolute value of x minus 6. But what we want to establish that this is less than epsilon. So we want 7 times absolute value of x minus 6. We want it less than epsilon. So what should our delta be? To get x minus 6 by itself, you divide by 7. We want delta to be epsilon over 7. And that's going to prove it for us. This was just the scratch work. Now we want to prove this formally. That the limit as x approaches 6 of 7x minus 1 equals 41. We have to show that for any epsilon greater than 0, if we let delta equal epsilon over 7, then whenever absolute value of x minus 6 is less than epsilon over 7, if that's true, then f of x minus L, we want to show that that's less than epsilon. Previously, we showed the work to show that this equals 7 times the absolute value of x minus 6. Because we're assuming this is less than epsilon over 7, that means that this is less than 7 times epsilon over 7, which equals epsilon. So we showed that whenever the first one is true, now this will be less than epsilon for any epsilon.